Hey, everybody. All right, I am going to try to get this to be big. Okay, I think I've got it fixed now. I'm gonna have to move that way. All right, so we're gonna go over the hepatic clearance quiz. Um, the clearance is the amount of drug cleared. First of all, use the same word in the definition, which isn't really a good practice, is it? Clearance is the amount of drug. Amount of drug. Is clearance an amount of drug? No. Clearance is the amount of blood that has all the drug removed from it per time. So clearance is not an amount of drug, is it? It's the amount of blood that has all the drug removed from it for time. So this is false. I really think it's very important for you to realize that clearance is not an amount of drug. It's an amount of blood. So liters per hour. Good. All right. Next. The maximum clearance of any organ is, well, we know that clearance is equal to blood flow to that organ and the extraction efficiency. We also know that the largest that the E can be is 100% or all of it being removed. So the largest clearance can be is Q, or blood flow to the organ. So blood flow to the organ is going to be the largest clearance or the highest maximum clearance that you can have is blood flow to the organ. In the case of the liver, it's hepatic blood flow, isn't it? Good. You said something like that. I should have given you credit. Drugs that are cleared by the liver that are low E drugs. Okay, so what does it mean to be a low E drug? Well, low E drug basically means that intrinsic clearance times fraction unbound is the rate limiting step, right? It's the rusty dairy. So clearance is approximated by enzyme activity and binding. So drugs that are cleared by the liver are low, that are low E drugs always have a relatively large F. Well, what else do we know about bioavailability? Well, we know that approximately 100% of it's going to make it through the liver. So does this mean that they'll always have a relatively large F? Well, it is true that FH will be relatively large. All of these fractions can only go between 0 and 1, right? Because it's between 0 and 100%. But we know bioavailability is dependent upon FA, FG, and FH, not just FH. If we know FH is 1, we still don't know anything about these two, do we? So it's not always. It could, but it doesn't always have to be a relatively large bioavailability, because bioavailability has two other components that could be low. Okay, so that's false. Now, Mr. Green Jeans, you probably don't know Mr. Green Jeans, but he used to be on the Captain Kangaroo show, which was a kid show I liked to watch as a kid. Is getting 400 milligrams, whoopsie, is getting 400 milligrams every 12 hours PO of drug Y, which is a high E drug. Well, a high E drug means the clearance is approximated by blood flow, and the fraction that escapes the first pass effect is approximated by Q over intrinsic clearance times fraction unbound, but this fraction unbound is seen by the liver as 1 because it's non-restrictively cleared. So, he's getting 400 Q12, which is metabolized by CYP2D6. So we know it's metabolized by CYP2D6. Mr. Green Jeans adds a drug that inhibits the activity of the CYP system, so it decreases intrinsic clearance. That's not going to affect clearance, but what will it affect? It will affect your bioavailability. If you decrease the intrinsic clearance, more of the drug is going to make it through that first pass through the liver. So how will you change the dosing regimen to compensate? Okay, well, CSS average is going to be equal to, in this case, it's PO, so bioavailability, bioavailable dose rate, all over clearance. Now, do we need to look at free concentration in this case? Do we expect there's going to be a difference between free and total concentration? Well, what's the only time we need to look at a difference between the free and total concentrations? Well, only if there's been a change in binding. And do we anticipate that there's been a change in binding? It certainly hasn't been put into this equation or into this problem. So we're going to assume no change in plasma protein binding. So we can assume we can look at total to determine what's happening with free. So what do we have to do? We have to come in here and replace these terms with more information that we know, because we know bioavailability is determined by FA, FG, and FH, which is approximated by Q over intrinsic clearance times fraction unbound, because it's a high E drug, times dose rate. So this whole piece here is the bioavailability, isn't it? And clearance in this case is going to be approximated by Q, because Q is the rate limiting step. So what's happened here is we've had a decrease in intrinsic clearance, which will increase bioavailability and therefore increase CSS average. So what are we going to need to do? We're going to need to decrease the dose rate, aren't we? So currently he's getting 400 milligrams Q12 or 800 milligrams a day. So we're going to decrease it to 400 milligrams per day. What about dose interval? Well, let's look at the half-life. The half-life is 0.693 volume, which is really all about the binding situation. None of that's changed that we know of. And the clearance, which is approximated by Q. Has any of that changed with this change in intrinsic clearance? No, it's not a factor. So we're going to leave it at every 12 hours, aren't we? But we want to give 400 milligrams a day every 12 hours. So we're going to break that 400 milligrams per day into 2 doses, and we're going to give 200 milligrams of drug Y every 12 hours. All right, now we have Bob White, who's getting 250 milligrams Q12PO of drug H. Now we have a low E drug. A low E drug's clearance is going to be determined by intrinsic clearance and binding. And the fraction that escapes the first pass effect is approximated by 1. And is metabolized by CYP3A4. Mr. White develops congestive heart failure, which decreases Q. So what's happened here? A decrease in Q. How will you change the dosing regimen to compensate? Well, let's see. CSS average. Do we need to look at free concentration? No, because we've had a decrease in Q, not a change in binding. So we're giving this orally, so we have to worry about bioavailability, bioavailable dose rate, all over clearance, which is going to be equal to, I'm going to just erase that, FA times FG times 1, because FH is approximated by 1. This should be FA, sorry, times dose rate, all over clearance, which is approximated by enzyme activity and fraction unbound in plasma. What's happened? A decrease in Q. So is a decrease in Q going to affect CSS average? No, so it's no change in dose rate. So our dose rate is still going to be 500 milligrams a day, isn't it? How about dose interval? Well, let's look at half-life. Half-life is 0.693 volume. It's supposed to be a T. All over clearance, which is approximated again by intrinsic clearance and fraction unbound in plasma. What's happened? A decrease in Q, that's not going to affect anything. So we're going to keep it at Q12 and we're going to just leave it at 250 every 12 hours, aren't we? We're not going to mess with it. Q is not, changes in Q don't matter because it's a low E drug. Which of the following are determinants of organ clearance? Well, let's see. FA, does that determine organ clearance? No. Fraction absorbed? No. How about fraction that makes it through the gut? No. Does that have anything to do with organ clearance? No. How about Q? Yes. How about intrinsic clearance? Yes. How about binding to plasma protein? Yes. Because we know that according to the well-stirred jar, we have clearance is equal to Q times E, and E is intrinsic clearance times fraction unbound all over Q plus intrinsic clearance times fraction unbound. So the three determinants are fraction unbound in plasma, Q, and intrinsic clearance. Now, if I asked you what determines low E drug cleared by the liver, you're going to say intrinsic clearance and binding. If I asked you if this was a high extraction drug, what's a determinant of organ clearance cleared by the liver, you'd say Q. Wait a minute. Wait a minute. Your patient is getting 500 milligrams. Whoopsie. Is getting 500 milligrams Q12 PO of drug A. This is another low E drug, which is metabolized by 2C9. Drug X. Drug X, a 2C9 inducer was added. So that's going to increase the intrinsic clearance of the drug. How are you going to adjust? Okay, so it's a low E drug. So low E means clearance is approximated by enzyme activity and binding, and the fraction that escapes the first pass effect is approximated by 1. So CSS average, do we need to look at free concentration? No, because we don't have a binding change. So we're going to look at total. So we're giving it orally. So we need to think about bioavailable dose rate over clearance. For a low E drug, clearance is going to be determined by intrinsic clearance times fraction unbound. And our bioavailability, our bioavailability will be FA times FG times FH, which is approximated by 1, times dose rate, all over intrinsic clearance times fraction unbound. And what's happened? We've had an increase in intrinsic clearance will increase our clearance, right? And therefore we'll have a decrease in our CSS average. So we need to increase the dose rate, don't we? Currently, they're getting 1,000 milligrams a day, so we now want it to be 2,000 milligrams per day. How about dose interval? Well, let's look at half-life. 0.693 volume, which is all about binding, isn't it? Divided by clearance, which is determined it's a low E drug, so it's going to be dependent upon enzyme activity and binding. What's happened? We've had an enzyme induction, an increase in intrinsic clearance, which is an increase in clearance, which decreases half-life. So we're going to go from Q12 to Q6, aren't we? So we're going to give 4 doses a day. So we're going to divide 2,000 by 4, so that's going to be 500 milligrams. Q6. I can't see this now, but it should say 6 in that. Let's see if I can move this. So 500 milligrams every 6 hours. All right, drug J. Drug J here, oopsie. Drug J, Fe is 0, which means it's totally cleared by the liver. Highly protein bound to AAG. And clearance is 12.7 liters per hour. So what's the E? Well, clearance is equal to Q times E. Clearance is 12.7 liters per hour. Q is 90 liters per hour times E. So if we divide 12.7 by 90, got an E of 0.14. So that's a low E drug, right? Now I can look at the number and know this is closer to 0 than to 90. And this is going to be a high E drug, isn't it? We can always do the math though, and we came up with an E of 0.14, so we know it's a low E drug. So drug J has had an increase in AAG, and it is bound to AAG, highly bound, so changes matter. So if there's an increase in AAG, what does that mean? There's going to be a decrease in fraction unbound, right? So what's going to happen? Well, in this case, do we need to look, actually, I'm going to erase some of this. So we have a low E drug. So clearance is approximated by intrinsic clearance times fraction unbound. And the fraction that escapes the first pass effect is going to be approximated by 1. So do we want to make a change in dose rate? Well, let's look at CSS average. But do we need to look at free concentration in this case? Well, has there been a binding change? Yes. What's happened is there's been a decrease in fraction unbound, so there has been a binding change. So we need to look at free, don't we? So let's see, and it's given PO. So we have to look at bioavailability, which is FA times FG times FH, which is approximated by 1 in this case, times dose rate, all over clearance, which is determined by enzyme activity and binding. And then we're going to multiply the whole thing times FU because we want the free concentration, don't we? So those are going to cancel, aren't they? And what's happened? There's been a decrease in fraction unbound. But that means there'll be a decrease in clearance, and then that will be balanced by this increase in binding in the periphery. So these two will cancel each other out at steady state. So there's no change in the dose rate because the CSS free should remain the same. Well, what would happen to our total concentration? Well, our total concentration, we would get rid of this, wouldn't we? This would be total. And so total, that decrease in fraction unbound decreases clearance, and we'd see an increase in CSS average total. So what is a team going to want to do? They're going to want to decrease the dose rate, aren't they? But we don't want to change the dose rate because the free concentration will remain the same at steady state. How about dose interval? Well, let's look at half-life. Half-life is 0.693 volume, which is determined by binding. And right away, we see this is going to decrease, don't we? And clearance, right? So it's going to affect both clearance and volume to the same extent, and there'll be no change in half-life either. So again, we don't want to change the dosing interval, do we? Tricky. Tricky. No changing. Total concentrations at steady state can be used to determine what's happening with free concentrations as long as the drug is being given intravenously. Well, no, total versus free has nothing to do with the route of administration or route of administration, does it? Well, what would this, so this is going to be false. As long as there has been no change, no change in plasma protein binding, right? We can assume that total can be used to determine what's happening with free as long as there's no change in plasma protein binding. That would make it true. But this statement has nothing to do with if you're giving an IV or PO, does it? The difference between IV and PO is all about F, which is FA times FG times FH. Be thinking about those things. There would be a difference between IV and PO, but not between free and total, right? It's mixing up some ideas. Well, I hope that helped and cleared up any misunderstandings you might have had. It seemed like this was an all or none kind of a quiz, like either you got them all right and a lot of you did, or you did poorly on it. And I want to make sure that you have a chance to straighten out your ideas here and let me know if you need more support. All right. Thanks so much. Bye-bye.